To investigate the security of quantum protocols, we have to think like an adversary. So in this video, imagine that you are Waldo and Wenda, and your goal is to break the security of position verification. So let's find an attack to our protocol using entanglement. So what does this mean, using entanglement? Entanglement means that Waldo and Wenda can share an arbitrary amount of EPR pairs. They've somehow exchanged them before, and they store them locally. Of course, they need quantum storage to achieve this, but let's say that I give you that. You are, after all powerful now. If Waldo and Wenda share entanglement, then Waldo could of course use this entanglement to teleport a qubit to Wenda. And this will be our trick number 1 to defeat security. It is useful to remember what happens in quantum teleportation. If Waldo wants to teleport a qubit psi to Wenda using this state, he will get 2 bits as outcome. So remember, what he does is he takes this state, or rather this and the first qubit, and performs a measurement in the Bell basis. This gives him 2 outcomes, which of course he would have to send to Wenda. But if he performed the measurement in the Bell basis and got outcomes A and B, then for outcome A and B, Wenda will hold the state x to the A, z to the B, applied to the qubit that Waldo wants to teleport. This is trick number 1. This indeed, the form of Wenda's state, brings us to the crucial trick number 2. Let me call this trick measure first, then correct. Suppose Wenda has x to the A, z to the B, applied to one of the BB84 states. So x is, as usual, the state encoded in the basis theta. So for example, Wenda might hold this state if Waldo tries to teleport a BB84 state to Wenda, but Wenda does not have A and B. She is, however, sure that she will learn A and B sometime later. So given that she knows the basis theta already, why doesn't she just measure the qubit? The question is, does she need to wait for A and B to arrive? That is, does she have to store the qubit to have any chance of figuring out x? Or can she perform a measurement first, and then when A and B arrive, she can correct her outcome to get the correct x? Indeed, it turns out that there's such a strategy for Wenda, given that she later learns A and B. If theta is 0, Wenda will simply measure right away in the standard basis. This gives her some outcome, which I'll call x tilde, and the probability of getting this outcome if I measure in the standard basis is just given by this. Namely, this is my basis element, and this is what I'm measuring. So note that here actually theta is 0, so this really is the standard basis. So note that whether I see x in A applied to x or whether I see it applied to x tilde does not matter. Indeed, in this case we can see that z is completely irrelevant, because z leaves the standard basis invariant. So indeed, the outcome that I will be getting corresponds to xa on x tilde. What happens if A now arrives? Since x is really just a bit flip, what Wenda can do is simply invert the outcome after she learns A. So let's say that she records A tilde, so her strategy will be that if she later learns that A was 0, then she's just going to say, well, x tilde is correct, there was no bit flip. Or if A is 1, I have to correct that, so I will say that x is equal to x tilde, x or 1. So I flipped a bit. So Wenda can definitely compute x. If theta is 1, she measures in the Hadamard basis. And the nice thing about this trick is that it works for both the standard and the Hadamard basis. So if theta is 1, Wenda measures in the Hadamard basis, and the probability of getting the outcome x is given as follows: x tilde in the Hadamard basis with x a z b x. So remember that in fact the bit flip does nothing to the Hadamard basis. So this is the same as x tilde in the Hadamard basis zb on x. So as before, you can think that the outcome is actually z to the b x tilde in the Hadamard basis. So remember that the operator z is the bit flip in the Hadamard basis. So if Wenda later receives b equals 0, she'll output x being equal to x tilde, and for b equals 1, she will again just flip her bit. You see that Wenda can thus measure first and correct later once she received the bits A and B. We are now armed with two very useful tricks. So let's use these tricks to break security. I will take n to be 1 here. That is, they will do this for just one bit, but the argument is exactly the same for many. At the start, Alice and Bob does have a bit x and the basis theta. Alice encodes the bit x and the basis theta and sends it to Waldo. Bob sends the basis theta to Wenda, of course believing her to be Waldo. So what does Waldo do? Waldo takes the incoming qubit and immediately performs quantum teleportation. Namely, he takes the state and he teleports it to Wenda. Meaning he measures in the Bell basis, getting two outcomes, A and B. He keeps A and B himself and also immediately sends them to Wenda. Wenda, at this point in time, already has the basis, theta, as well as XA and ZB applied to the basis element, namely X encoded in the basis theta. So now it's time to pull our trick number 2. Wenda simply measures in the basis theta to get an outcome tilde x. She immediately sends theta and tilde x to Waldo. Now, once the messages arrive, both Waldo and Wenda have A and B and theta, as well as tilde x. And we already saw in our trick number 2 how from all of these things together we can in fact compute the right x. Waldo and Wenda thus perform this computation and send the resulting bit x to both Alice and Bob. Note that our trick 2 definitely worked. So since they sent the right bit, they will actually pass the test. Do they also pass the timing test? Note that the timings that Alice and Bob will observe here are perfectly consistent with Waldo claiming to be at this position here in my example. So they certainly managed to cheat. So security in this protocol can only be attained if we somehow limit the entanglement of Waldo and Wenda. Of course, you might be asking, maybe there's a smarter protocol out there. It turns out that no protocol can be secure if Waldo and Wenda share an arbitrary amount of entanglement. And you can find many pointers to the literature in the lecture notes, which will tell you why. Here, let's now focus on our simple protocol. In particular, let's go and show that the simple protocol is indeed secure if Waldo and Wenda's entanglement is limited.